Just a little bit about me. I'm mostly focused on infrastructure engineering, and I'm really into Rust right now. Kind of jump all over. I've been using, my first use case with Salt was 2014. I deployed an Elasticsearch cluster with a RabbitMQ cluster, and then I never really did anything with Salt after that. And then last year, someone came to us and was like, we should do Salt in production. I was like, that's a really good idea. And so I've been doing Salt infrastructure since 2017. We've been trying to get Salt where we want it. So we've submitted some upstream patches. I think the most significant patch is adding a new master type, which was distributed, which does an internal load balancing hash. So you don't need an LB in front of there's a master infrastructure. It's all hash-based. I got to do the obligatory views are my own. Don't represent anyone else. And then some of the topics I'm going to breeze through, and I know they're really deep, like IPVS. I'm going to just say, oh yeah, we use IPVS, but you don't know you might not know what IPVS is, and you might want to know how we configured it. So just grab me after. Okay. So kind of, if you didn't get it from the first slide, it's about scaling Salt. And I'm not talking about load average or the number of minions. Those are nice things, but that's not really what I mean about what I mean when I say we're trying to scale Salt. What I'm trying to convey when we're trying to scale Salt is the workflow, right? Because at the end of the day, the interface that folks have into Salt is the workflow. And so, the new thing nowadays is Git-only workflows, and we've been doing them for a couple years in our team, so it's not really new to us, but now everyone is getting into the Git ops mentality, and I think they sort of munge it with function as a service or Lambda, but really for us, it's really just Git. And then kind of dealing with multi-tenancy at every layer, which other folks really don't generally get into. I'm not just talking about environments where you set up file roots and you have environment A, environment B, and you have pillar roots and you have environment A, environment B. Talking about on the OS, on the system, tell me how you do isolation on the OS. How many are familiar with the kernel get wrecked series of attacks? The eBPF attacks? Right. So just kind of describing what we offer internally. We only offer an API into Salt. We do not offer the Salt command at all in our infrastructure. It's just too dangerous. Also, there's a lot of ACLs and authorizations that we couldn't really get into just a Salt command, even if we passed in PAM tokens and so forth. It's just not working. What we do want to offer is Salt, the command channel, most of the features of Salt, especially beacons and reactors for monitoring, and a 100% Git workflow. In other words, you don't know anything about the Salt infra. Just real quick about our Minion configuration. We started off with UDP and the standard base Salt setup for Minions, and then we're this is really inefficient, and we keep getting Minions offlining every now and then. So if we switch over to TCP, it's been great with Python 3. Don't try to run TCP on Python 2. We're on 2018.3, so we're pretty up there. I think we're on .2. I can't remember. And then we run master type distributed, which I kind of alluded to earlier. That was a patch we submitted. And kind of a break from how most of our infrastructure services are set up, we do not have a load balancer, and there's no SNAT. We literally just have a list of masters and they're direct connect. And I think for a lot of folks, that's probably just how you guys always set up Salt. But for us, because we're multi-data center, because we have N+2 requirements, moving away from LB was actually a pretty big thing. And actually, we tried to put an LB in front of it. We actually got bit with secret exchanges. I don't know how many of you know this, but there's a separate secret for the connection that's negotiated with the master. And if your minion is connected to that master and then it runs state, high state, or opens up a returner, if it connects to another master with a different secret, the whole thing like goes into a loop. And it's generally not bad. It's generally bad. And onboarding a minion is really easy. You have the salt package, you pass in a standard endpoint for your master, and that sets up the rest of your minion, including the list of masters. So we run salt masters, and we don't run masterless for a variety of reasons. But one of the issues we have with running salt masters is that each master is only capable of handling a certain number of minions, whether you reach OS limits or you reach Python and salt limits. We can only handle n minions. And so the moment we try to do multiple masters to onboard more minions, you guys all know what happens, right? Well, if you want to run salt commands, you got to go to this master, and then you got to hope that the minion is connected to that master, and so management becomes an issue. Then, even if you figure all that out, you got to aggregate all the data. Like if you're running CMD run, like you got to figure out where are all the results. You got to aggregate them. And adding masters is really hard because the more masters you add, the worse the problem becomes. So actually the salt guys thought of this, and they have master of masters, or if you set it up with multiple master of masters, it's masters of masters. And they talk to syndics, and the syndics talk back to the masters of masters, and this creates a great workflow. You can go to a master of master and execute a salt command, and everything works. Like, it's amazing. Until you hit like 3,000 minions and you're like, oh, the message bus is congested and this does not work so well anymore. And so like this is the problem we ran into in production, and we just could not get away from this message bus congestion. And we tried tuning the message bus as much as possible, but just couldn't get there. So we kind of decided that, everyone's talking about decentralized currencies and all this. Oh, we try some like decentralized topology. So the idea was that instead of these masters talking to a master and having a bidirectional flow, we just make it like unidirectional, where the master just talks to like some unknown, yet to be implemented layer, with no idea what it is. That's why there's 3 question marks there. And the minions talk to the master. So if we want the master to do something, it'll just like check into this like place and go do that, and then return the results back. And it's just one way. It's not that this mysterious thing like can talk to the master itself. It doesn't work like that. Okay. So we ended up creating the Salt API Proxy. It's an in-house solution, and I don't think it'll ever be open source. And in a way, it doesn't need to be open source because I was told 2 months ago that apparently this is exactly what SaltStack Enterprise is. So what SaltStack Enterprise is that it's basically a little agent that sits on every master and then does orchestration for the master. Thereby, every Salt master is totally orthogonal to every other salt master, and no one is talking to anyone, and that's how you get the scale. But kind of talking about our API proxy, we maintain like which minions are connected to which master. The masters, because it's a one-way flow, they just check in to say like, hey, what jobs do I have? So like what jobs do I have to execute? So let's say your API, like let's say you want to run CMD run. You go to our API proxy, you log in with LDAP, and that's just all curl. You just pass in your credentials, and it just creates a record in our API. Then a master will come along, execute some part of that, depending on which minions are connected to it, push the results back, and that's that. The API proxy never talks to a master directly. It's all one way. Also does like things like key management, and it allows masters to register themselves into the proxy. Okay. One of the other nice things about this is that, kind of alluded to that earlier, is that it's all integrated into LDAP. So here's the premise. You can run anything with Salt as long as you have sudo access in LDAP, right? Because if you have sudo access in LDAP, you don't really need Salt anyway. But this is like the gatekeeper. Like LDAP is still our gatekeeper, and we ended up not doing this with the LDAP module in Salt because it doesn't support things like NIS netgroup triple or the idea of sudoers. So it was nice just to be able to implement it at the proxy layer. It's also integrated with our asset database where we put all the servers that we have. Okay, this last point, that it's NAT friendly, and I will explain, well, it'll make more sense like on the back half of the presentation, why it has to be NAT friendly. So question marks are filled in, right? So there's this API proxy. On every master, there's a little API service that's running, and the masters just only know about the minions connected to them, and the masters do not know about any other masters in the infrastructure. That's how we get Salt to scale. Okay. So how does a minion get onboarded? Well, see, there's a stork and there's a provisioning. There's provisioning, and we actually have like 3 different provisioning systems. I don't know. We have 3 different provisioning systems, but the key is that they all insert like whatever they provision into this asset database, whether it's bare metal, whether it's a VM, whether it's a Kubernetes pod or service or deployment, whatever, it all gets registered into this asset database, and it makes our life really simple because when it does the Salt call, our Salt master just has to go to our asset database and say, tell me what you know about this minion. Then that Salt master does API calls into GitLab, and if it's a environment we never seen before, and by the way, we have thousands of environments, and we get it, like I think the average is like we had like 20 to 30 environments a day, something like that. It creates a GitLab project, it puts some skeleton states in there, and it sets up all the ACLs in GitLab. Then the Salt master clones the repo, adds the environment, it sets up the minion just through state high state, and then finally the minion is registered into the Salt API proxy from the master. Remember that arrow just goes right into the API proxy? The API proxy doesn't try to probe and see what minions are connected where. It's just the master says, hey, I'm connected, this minion is connected to me. And I was trying to get to like 100% Git workflow because I just don't want people to know about the Salt infrastructure. I just don't think that's how you get scale with Salt. I think you just got to let people work with what they know, which seems to be Git. So we use GitLab, and we just have a common GitLab namespace. And inside of each repo, we support the notion of states, pillars, reactors, beacons. And this is kind of what it looks like. It looks like your serve Salt path. Like it just sort of looks exactly like it would. We support beacons through pillar data, but that wasn't supported till 2017.7 well. Yeah, we also support reactor.com. We also support dynamic module distribution because inevitably someone comes up and says, I would like a custom grain. And we're not going to install that on our masters. We're just going to let them define it. So support dynamic module distribution, and then that enables custom grains, modules, and so forth. The workflow is very simple. You auth in, you clone, you git commit, push, you auth back out, you auth again. The master pulls down those changes. It services things like state, high state, it services returners, it services beacons. So this is all really nice and well, and it's really powerful, but it's actually really insecure. And I think if we tried to deploy it out as it was, you would be in a world of hurt. I think the one thing that sticks out to me is that Salt states can be all Python. and it's not sandboxed. And then the salt master is running as root, and like every thread is running as root. And that becomes a problem because it's a privileged command channel, right? Like salt minions are running as root because you don't know exactly the privileges they need ahead of time, so we just all run everything as root. In fact, the salt docs say that you should just run masters as root, okay? So this becomes a problem because all of a sudden, you could have one environment start to reach across boundaries and look at what's on the master, look at what other tenants have on your master, and even worse, they could just issue salt against a different host that's connected to the master. There's no isolation. Everyone with me? That's the problem, like that bold text. But it's never, this is how people are going to run it. That's how it is. The multi-tenancy is not about supporting multiple tenants. I lied to you guys in the beginning. It's not about that. It's about isolating them. And it's not like you can just go to Tom Hatch and be like, hey, Tom, can you like implement multi-tenancy in Salt? Because that's the wrong place. It can't be fixed there. It's just not the right place for the isolation. So it's not like, I'm not trying to put SaltStack down or anything. It's not the right place to fix it. So I'm sure you guys are familiar with like just configuration-based environments, like statically defined environments. You have file roots and then some environment, and it's pointing to some directory. And you can have pillar roots, and you can have like external pillars. But like external pillars aren't like really Git friendly. And you still like run into a lot of challenges running infrastructure because every time you add an environment, you have to restart the master. If you have new new reactors, you have to restart masters. And we still don't have isolation because everything is running as root. So in an effort to try to address this, we tried to create a patch internally, which crashed and burned like pretty quickly. I'll share the failure. It was to try to create like this dynamic base environment. So every time a minion would check in, right? Once we figured out the minion ID, we would like change the salt config variables so that the base would be pointing to that environment's directory on the master. Well, then I found out as things went along that it worked great when it was one master and one minion, but the moment you added two minions, you ended up getting like thread safety issues. You ended up getting like file system, the Salt internal file system cache being busted. And it really didn't fix anything. I think I just wanted to see if we could do it, but it really didn't fix anything because updates still required restarts, like adding new reactors, still required restarts, like full restarts, and there's still no isolation. So ultimately we realized that every tenant needs its own master. And then the question becomes, how do you deal with that? Like when you have thousands of tenants and you have tenants coming online all the time. I like to turn my phone off at night, so I'm not gonna do it. So what we really needed was master orchestration, where if there's a change for an environment, it goes out, it updates the masters, sort of just is magic and it just works. Was that saying like, you know, if it's working well, it's just magic, right? Like it just has to be magic, like it just has to work. And then obviously we need isolation and density. This is a key one that people forget. I think there was a VP from First Data at the keynote. She was talking about how Microsoft went from like thousands of servers to 1 million servers. Yeah, I don't think I'm gonna get 1 million masters. So you just need density, right? And on top of that, you need master endpoint reliability. And in other words, every tenant can't have its own master endpoint. We need to have like, let's say 20 master endpoints and they need to just work for everyone. That's what we needed. So we looked at virtual machines, like the OpenStack route, and kind of looked at them, and I'm sure most people are familiar with this. I'll just go over it. You have a compute, you have the hypervisor / kernel, and then you have the VMs, and they themselves have a kernel, and then you have a master running inside the VM. I think most people are familiar with this. It's really nice because it has great isolation. It really has the isolation that we're looking for because it's isolated in hardware. Unfortunately, just because it's isolated in hardware doesn't mean it's automatically secured. There was just this side channel attack, I think a few weeks ago, where they were exploiting like the L1 data cache. And they exploited it, and they could all of a sudden bypass VM boundaries. Okay, so those things happen, but they're far and few between. The problem with virtual machines is that it's an actual machine. You get a full operating system. They're heavy and they're slow to provision. They're also difficult to orchestrate because it's easy to spin up a VM and spin down a VM, but to actually orchestrate like the network side, to orchestrate the network and the service side, it's a little harder. Then, because they're heavy, you run into density issues where you can only have so many VMs per host, right? So what you start to do is do things like overcommit memory, right? We've all done that. And just kind of cross your fingers and hope no one ever goes over, I don't know, whatever RAM threshold you pick. But one of the nice things about VMs is that security trusts them because a lot of infrastructures run on VMs. They're well understood. They're production ready. It's kind of not cool. I don't know if that's the right word, but we started looking at containers because everyone loves containers, right? Containers are going to fix everything. And with the container setup, you have your OS, and you have the OS actually managing the containers. They share the kernel address space. A lot of people don't realize this. This is actually a huge shortcoming of containers. It's also why they're so great. Because even though they're sharing the same kernel space and they have poor isolation, they're really fast and light. Because every time you spin up a container, you don't have to spin up an OS. You don't have to spin up a kernel. You don't have to, you just have PID 1, right? I mean, it's like one process, you're done. Now, PID 1 could take a long time, but on the surface, containers are great. They're just difficult to orchestrate, and I would say they're production ready. I mean, Google's been running containers and C groups for a while, and now we have C groups 2 coming out. They wouldn't have 2 if one was rock solid, right? They would just give up, right? Anyway, but they have fewer density issues. That's good. It has efficiency. You can't really fix efficiency. Efficiency is either built in or not. But what you can fix is isolation. So just kind of drive home the point. If you're running Kubernetes and containers, this is what it looks like. You have this huge attack vector across all the pods or containers that you run, which is the kernel space. And don't say the kernel never gets hacked, because that's exactly where the hacks are coming from these days. Get wrecked. This is an attack against all the eBPF stuff that was added by Facebook, right? Where people are doing privilege escalation and so forth. It'll happen. So in order to fix the orchestration problem, we started looking at Kubernetes. And Kubernetes is nice because it has network orchestration. It has this idea of deployments. And it has a lot, and I mean a lot, of different types of resources that range from storing secrets to shared storage. It's all Docker-based. They provide fast and light Docker container orchestration. And we get density, right? We can say, in Kubernetes, we can say, hey, I want to deploy 9 replicas across our Kubernetes infrastructure, and we're going to get 9, but they're going to be packed in. The problem with Kubernetes is because it's still all container-based, we still need isolation. So because this is all kind of new for us. There's this thing called Kata Containers. And it was based on Intel's Clear containers that I wouldn't say they abandoned it, but they moved over to the OpenStack Foundation and rebranded themselves as Kata Containers. And it's nice because it is just a container runtime for Kubernetes, so it's sort of drop-in. And what's interesting about it is that it runs a QEMU Lite VM for each pod. So now you get like that VM level isolation, but it's a light VM. In other words, there's not a full operating system. You don't have systemd, you don't have like cron or add-d, like none of that stuff is there. It's still light, it's still pretty nice. It's still like light. If you do docker exec uname with C groups, with like containerd, or with the Kata runtime, the spin up times are like, it's like half a second difference. Like no one's gonna care about half a second. But what people will care about is isolation. Because remember, this is your command channel, and if you don't have isolation, it's gonna be really bad someday. And the other nice things is that there's other optimizations that make it very conducive for running saltmasters like KSM, which is a kernel same page merging. So here's the idea. You have 10 pods on a host, on a metal. What KSM will do is it'll try to dedupe all of the pages it can in physical memory. This is nice because if you're running 10 saltmaster pods, a good chunk of those pods are going to be running the same application code. It's going to be running the saltmaster. It's going to be running the kernel for that pod. So that's how we get even more density, right? By the way, that KSM bit, I don't believe it exists for C groups. And performance is on par, or sometimes better than C groups. And I'll say sometimes better. We've seen better network performance with Kata containers than with C groups. So I totally copied and pasted this because they did a better job. Containers in the cloud today, and this is how they're all solved with Kata containers. You have an individual kernel per Kata container, per container. And that's really big break because what you can do now is start to move pods around and move containers around without wondering how they're going to interact with the underlying kernel, and vice versa, where you can upgrade the kernel of your pod, of your container image, without worrying without waiting for the your administrator, your Kubernetes administrator to get you there. So like, let's say I want to run 4.19, because 4.19 has network package batching, and that's gonna add, that actually like improves throughput like 35% in the Linux kernel, and I want 4.19. Well, if I'm running a typical Kubernetes instance or setup, I have to wait for the folks running Kubernetes to actually deploy 4.19, and they're never gonna do that because they're gonna be like, oh, that's not an Ubuntu kernel, or it's not a Red Hat kernel, and we don't wanna support it. So then I'm stuck. But if I have this notion that every pod or every container ships with its own kernel, I can go to 4.19. Pretty nice. So Kubernetes saltmasters. So the way we treat tenants is in every tenant is a Kubernetes deployment. How many are familiar with the idea of deployments in Kubernetes, just real quick? Okay, I'll just describe it real quick. Deployment is just like a unit, like an application, right? I think in the older days, people would define pods. Like maybe if you saw some Kubernetes YAML, it's like pod, it's like the resource type. Deployment is a little more than that. It's more holistic because it allows things like upgrades and rolling upgrades and rolling rollbacks. So each tenant for us is a Kubernetes deployment and a service endpoint. How many are familiar with service endpoints in Kubernetes? It's the same people. All right. All right. Anyway, so if you guys have questions about any of this, just grab me after the talk. Kube router is what we actually use to manage the service endpoints and to do round robin and pod networking for our Kubernetes deployment. But the actual orchestration is all handled by Kubernetes. We did not need to use kube router. We could just stick with, I don't know, something else. But we decided to go with kube router just because it had IPVS support first. How many are familiar with IPVS? Sorry, I'm giving you guys like a workout. All right, cool. All right, thanks. So this is how we define the deployment and service, right? So we have this YAML file, and it gets generated by this simple bash script, which is just talking to GitLab and pulling down the list of tenants, right? And the only difference, like, between each tenant is this commit reference. Like, that's why it's in red, just to drive home the point. It's basically just this latest commit reference. If you're not familiar with Kubernetes, one of the nice things is that once this is defined and it's loaded up, you can go and edit it. And every time you edit that deployment or service, it'll upgrade and orchestrate that upgrade for you across all the Kubernetes, all the kubelets. And just real quick, what's inside the pod, right? So you see here the command is run.sh, and that's very descriptive. What all that's doing is starting up a saltmaster. And inside of each pod, you just have serve salt. And under serve salt, it's just Git cloning right out of GitLab. That's all it is. Like, exactly what you guys saw in the Git structure is what ends up in serve salt. There's also, but we because we have to, because otherwise I wouldn't have a job. So there's like a common minion.sls that also configures minions for us at state and high state. So that gets pushed into serve salt /salt. Obviously you need saltmaster packages because you're going to be running saltmaster. I will say one thing. We did need to tweak the Arena library for Salt. Salt depends on the Arena allocator. And for Python 3, the Arena library maps everything as shared pages. But because we're running these pods inside a hypervisor, you can't actually map shared pages across hypervisor boundaries. It's this whole thing. But it's some security feature. They just won't let you map shared memory across hypervisor boundaries, which actually kind of makes sense. But we just had to change that to private. That was the only thing we had to do. Otherwise, Saltmaster works great with Kubernetes, just as it is. And run.sh, the most descriptively named bash script ever, is the entry point, and it starts Saltmaster, and that's all it does. Okay. So to master orchestration, kind of hinted at this. Every time the environment changes, let's say a tenant goes in and makes a change in their state. That's a new commit hash. That commit hash makes its way down into the Kubernetes manifest, and kubelet is looking at that manifest and saying, are there any changes? And the moment there's changes, there's a background rolling upgrade that kicks off. And once that rolling up, once the new pods are provisioned, it just simply switches a service endpoint. In that way, you don't have this janky process where someone makes a change and then all the master infrastructure goes down, and then magically it's alive again in 5 minutes, and everyone is wondering, well, how did that happen? So we're trying to just use Kubernetes for upgrading the whole deployment. Kubernetes also has built-in probes and monitors, so it's also checking the liveness of those masters. Maybe there was a sec fault or something like this. All of the monitoring is built into Kubernetes. sort of one of the things we needed was that ability to have generic master endpoints, and we got that through this sort of rotation of the pods underneath the service endpoint. So there we can basically have reliable endpoints on the Kubernetes side. 5 minutes? 10. Wow. All right. I better speed this up. All right. So just thanks. So just real quick, this is what an existing YAML deployment looks like, right? You see that pretty hash there? Oh, wow, it's so nice. And then when you upgrade it, right, it changes to the next hash. Kubelet will take care of all of the upgrades after that for the deployment side. Just jumping back to the API proxy request, I was hinting that it was NAT friendly. It is because of Kubernetes, it has to be NAT friendly, because all of the pods are networked with a class C, like 172. And one of the things that we exploited in handling these API proxy requests was a lot of the work that Garrett did. Who's familiar with Garrett from SaltStack? Yeah, he's a good guy. He did a lot of work on, on the scheduler. And so if we didn't have the scheduler, this would actually be really difficult because we have to run this sort of like tell me what to do job as often as we can. And so if we didn't have that, we would need like cron or we would need at. And in order to get those things today, you need systemd. And in order to get systemd, you need like the whole system. So yeah, it was going to be a mess. But we just ended up using the scheduler in Salt, and that saved us a lot of time. And it's far more efficient. So the minion master configuration, all the minions are routed to generic masters. On those masters, you have a forward rule, which talks to a localhost endpoint, and that localhost endpoint is an IPVS endpoint. Behind that IPVS endpoint is round-robin service endpoints for Kubernetes. Okay? And just an important fact, just because you have an environment, there's a lot of tenants that only use Salt as a command channel, and they don't care about states, they don't care about pillars, they don't get their own master. We actually just loop them into the generic master pool. So kind of like like a chart of it all. So minion comes in, the masters check, like, does this minion actually belong to a changed environment? If it does, then it gets forwarded out. There's a local forward rule to the IPVS round robin setup on that master. That IPVS round robin setup is pointing to the Kubernetes services. And KubeRouter has another IPVS round robin pointing to the actual pod. So there's like 2 levels of redirection. But we don't care because it's all NAT friendly. You can have like 5, it doesn't really matter. And obviously the simple case is if there's no modified environment, the generic pool of master services the state high state. Okay, so real quick, now you get like an isolated, more secure Salt master infrastructure. The tenants only need to know Git and Salt and beacons.com or reactors.com, that's all. And they use HTTPS curl friendly APIs to interact with Salt. No Salt command, no SSH access. I think right now there's like an ongoing effort within Salt and with us to get more CIS policy in Salt, like HubbleStack. 5 minutes? Okay, perfect. And I didn't mean to like rag on Salt at all. Like the stuff we encountered in terms of issues with multi-tenancy and isolation, that's applicable to any application. It's not specific to Salt. Just this is how we solved it. There's nothing Tom or Mike could do. It's not their fault. All right, and Q&A. Hi, yes.
How does the commit reference get updated in the Kubernetes deployment file when new changes pushed to the repo?
Okay, so I think the question was, I'm sitting here with this YAML file, how does this actually get updated? Okay, it's just a shell script, and it's just literally curling the GitLab API to get the latest hash of the repo, and then it just literally does a sed. Like, It's simple. Like, it doesn't have to be complicated, right? It is what it is. Yeah. Hi. The question was, I look at LXC. Yes, and I love LXC, but it's a political battle because it's not Kubernetes friendly. So I think there was some effort by an Ubuntu team member to actually make it Kubernetes friendly, and then I don't know what happened, but yeah. Yeah, I'm a big fan of OpenVZ. I know, yeah, you like it. Hey, yep. Oh. Yeah. Yeah, the question was, what other tuning did we try before just going into this crazy new architecture? We tried things at the TCP layer, window sizes, the basic stuff. We tried even jumbo packets. We didn't think that was going to be a problem, but we tried it. We tried increasing backlogs both on the job bus as well as the kernel. We tried as much as we could try, but ultimately it's sort of like a losing battle because what you're going to lose, even if you win, that particular like issue is that there's no isolation. So like even if you get like a really optimized saltmaster, right? Ultimately everything is running as root, and the only way to combat that is to like set EUID every tenant as a separate handler thread, right? But that would require way too many changes to saltmaster to get right, and so we just didn't. We tried a couple. We tried that patch. It was fun to write, but not so fun to run. Does that help? Yeah, yeah, pretty much. The bus is the pro. I don't think I can fully disclose, but it's 6 figures. That feels good, 6 figures. No, and no, it's 6 figures. Yeah, yeah. The gentleman behind you had a question. Yep. The question was, how many common components like pillars and formulas do we have across these different tenants? Because at some point, 2 tenants are going to want to manage SSH, right? So do we provide an SSH formula? Yes. So what we do is we don't only put common, that minion.sls into the pod. We also put like other things inside of that pod that we consider common, like LDAP. LDAP is a good example. Every Minion at the end is managing the LDAP configuration for that, for that Minion. That is in, that gets pushed into the pod. Does that help? Okay. There's like a common environment for that. I'll explain more. Hi. Yep. Yeah, that's right. You nailed it. So the question was like, does every tenant get its own Git repo, and then they can create their pillar data and whatever dynamic module they want? Yes, that's exactly right. So then how does that get pushed up to the master? There's just like, it does. So when the minion for that environment checks in, that the master like queries the asset database and says like, tell me which tenant this is. Like which tenant does this minion belong to? And at that point, it either creates the skeleton repo or it clones the the one that is already on record. That help? Cool. Hi. Yep, way in the back. It depends on how many calls I get at night. No, the question was how many of your tenants troubleshoot tenant issues? I'd say I think in the beginning we had a lot of troubleshooting going on, but it's been better now. Most of the time, most of the troubles we have right now are with Kubernetes, where like pods just refuse to get created. Then we have to go look what's happening. Oh, like this resource is out on the host, or someone deployed kubelet and didn't forgot to turn off swap. Things like that. But so far, it's pretty. Like it's getting better with time. I'm not going to pretend it's perfect, but it's getting better with time. No, because the moment they get on a Kubernetes host runtime or on a kubelet host, they can do whatever they want. They can just Docker into that pod and then, like, start issuing salt commands. So yeah. More questions? Am I getting kicked out? Hey. Yeah. It doesn't. So what ends up happening is, because we don't really need the full Git repo, because remember, like every time that pod spins up, right, it's a fresh slate. So we really don't need the Git repo to be more than just a copy. We don't need versioning, right? So we just end up overwriting the old stuff with the new stuff. Because like we don't need the Git pull. We're not doing Git pull in the pod. Sorry, I'm getting kicked out. All right, I'll be here. All right, thanks guys.